Good morning. Today, I'd like to talk some about the notion of a derivative of a complex function. To get started, let's go back and remember what happened in previous cases. In the first semester, we thought about the slope of the tangent line problem, and we looked at this limit. The limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. If that limit exists, we give it a name. We call it f prime at x0. This has a couple of hidden implications. First of all, obviously, for this limit to exist, f of x0 must exist. Otherwise, the arithmetic makes no sense. Also, though, the delta x could be large or small or positive or negative before we take the limit. F of x needs to make sense for all x's that are close to x0, that is to say, x0 plus delta x. There's more to it than this even, as we'll see in a minute. If this limit exists and is equal to this f prime at x0, then for small values of delta x, the fraction has to approximately be f prime at x0, with the approximation becoming better as delta x tends to 0. The difference between the fraction and the actual value of the derivative must be some quantity, which I'll call epsilon, which tends to 0 as delta x tends to 0. You can rewrite this as the actual difference in function value is this number f prime at x0 times delta x plus epsilon times delta x, where epsilon tends to 0 as delta x tends to 0. In Calculus 1, you called this quantity delta y. You called that quantity dy. The usual limit definition is equivalent to delta y equals dy plus epsilon delta x, where epsilon tends to 0 as delta x tends to 0. In third semester calculus, our previous discussion motivates the definition of differentiability. We say that f is differentiable at the point a comma b if the following statement is true. If the difference in function value starting at ab and ending at some location a plus delta x, b plus delta y, is equal to the partial derivative of f at ab times how much you changed the x plus partial of f with respect to y at ab times how much you changed the y plus epsilon 1 delta x plus epsilon 2 delta y, where epsilon 1 and epsilon 2 tend to 0 as delta x and delta y tend to 0. We called this delta z because we were plotting the function values on the z-axis. We called this dz. So we say that a function is differentiable when delta z equals dz plus epsilon 1x plus epsilon 2y. Working directly with this definition is really complicated in most situations, so in Calculus 3, you proved the following statement. If the two first-order partial derivatives of f are continuous at ab, then f is differentiable there. This is a much easier thing to work with than the definition is. For example, if f of x and y is x cubed y squared plus sine x cosine y, it's easy to calculate the two first-order partial derivatives. Since these are sums and differences of products of continuous functions, both of these first derivatives are continuous everywhere. That tells me that the f function is differentiable everywhere. Even though I can't draw graphs of functions of a complex variable, because I would need 4 dimensions, what I can do is I can argue by analogy. If you give me a complex number, z0, which I'll call a plus bi for its real and imaginary parts, if I have a function of such a complex variable, I can look at the function at z0 plus delta z. Now, z0 and delta z are complex numbers now, but we've established how to add things like that, so that's fine. F of z0 plus delta x is a complex number. This is a complex number. We know how to subtract complex numbers. Delta z, generally speaking, is a complex number, but we have established how to divide complex numbers, so that's not an issue for us either. If this limit exists, I'm going to create an abbreviation for it. I'm going to call it f prime evaluated at z0. This will be my definition for the derivative of a complex function. Doing the same manipulations as before, I'm going to say that f is differentiable at z0 if the following statement is true. The actual change in function value is the derivative at z0 times delta z plus epsilon delta z, where epsilon tends to 0 as delta z tends to 0. It should be noted, though, that this epsilon and the z0 and the delta z and the function values and the derivative values are all, generally speaking, non-real complex numbers in our new situation. The reason that we spent some effort earlier establishing properties of arithmetic for complex numbers is so that I don't have to do too much justifying when I look at the derivative. If I have a function of a complex variable, z, and that function is f of z equals z squared, which would be a plus bi multiplied by itself, then every step that you did back in first semester to find the derivative of x squared is still valid in the new context. The derivative of z squared is 2 times z. Evaluate that at z0. 2 times z0. At this stage, it might seem that this is just ridiculous because everything will obviously work the same. In particular, that business about continuous partial derivatives, one hopes that if the function that you're looking at has continuous partial derivatives with respect to x and y, the real and imaginary parts of our complex numbers, you would hope that that will be enough to guarantee that the function is differentiable. In an effort to be more relatable, given a complex number z, I can think of it as being a real number x plus I times some other real number y. My f of z I could think of then as being f of something that depends on 2 real numbers. F typically is a complex number, so it will have a real and imaginary part of its own. So one way that I could represent these kind of things is u plus IV, where I'm thinking of the u and the v as ordinary real functions of two variables. Let's look at an example. Let's look at f of z equals z conjugate. If z is x plus iy, then the function value will be x minus iy. The individual functions x and minus y have continuous partial derivatives, so our first thought is to think this must be differentiable. On the other hand, we have the same issue that we had in third semester calculus, except that it's worse now because we have more algebraic structure involved. I can get close to z by a wide variety of methods. There are many directions that I can get close to z0 here. If the derivative at z0 exists, it shouldn't matter which manner that I approach z0 in, I have to get the same rate of change. If I think about approaching AB using only points that have the same imaginary part, or in my picture, the same y-coordinate, then writing out the limit is straightforward. I end up taking the limit as delta x gets really close to 0 of delta x over delta x. Since delta x isn't 0, that fraction is 1, and I'm taking the limit as delta x goes to 0 of 1, which is 1. Therefore, the derivative of the function must be 1. Now, if you want to be a little bit more careful about it, you would say this. You'd say, if the derivative exists, it's equal to 1. But surely there can't be any complications. Let's look at another situation. I'm going to get close to the point of interest by leaving the a constant, the real part, the x-coordinate, and only varying the y-coordinate, the b part or imaginary part. Let's write down the fraction and then take the limit of it. Approaching along this vertical direction, we do a calculation that's very similar to the one we did previously, and we end up finding that if the derivative exists, its value must be -1. This contradicts what we just saw a moment ago that said if the derivative exists, it has to be 1. This is a contradiction. On the face of it, there is no single number that these difference quotients start resembling as you make the delta z go to 0. Our conclusion then has to be that f of z equals z conjugate is not differentiable regardless of where you're sitting at. This is very odd because if I write f of z in terms of its x and y parts, the real and imaginary parts of the complex number, x in the context of third semester calculus is differentiable. It has continuous partial derivatives. So does -y, but that's not enough to save us here. The difference between what we're doing right now and third semester calculus is this. In Calc 3, we didn't have any notion of dividing by a vector. In our new setting, we do have a notion of dividing by a complex number, and that complicates everything. I'll think of f of z as having a real and imaginary part. F of z is u of z plus iv of z. Z is x plus iy. I'll think of that as being just a pair of numbers so that I can represent this in some sort of format that's a little bit more familiar looking. If the function is differentiable, then as delta z tends to 0 plus 0I, regardless of how that approach is made, I have to get a common value for all such approaches. So we're going to look at two particular ones. If I rearrange what happens when delta y is 0, I end up with the limit as delta x tends to 0 of this real quantity plus I times that real quantity. We are examining the situation where f is differentiable. This limit has to exist. That means the limit of the real part and the limit of the other part must exist. If f is differentiable, the derivative must equal this quantity. On the other hand, there's many other ways that we could get close to the point a, b, so let's look at another one. If I do the same kind of manipulations as previously, I find out that if the derivative exists, it must equal this quantity. I now have two completely different looking formulas that tell me the value of what this derivative must be. So let's compare the two. For brevity, I'm going to omit the evaluated at AB here. The first formula is what the derivative must equal. The second formula is also what the derivative has to equal. Those two things have to be equal to each other. Each is a complex number having a real and imaginary part. For these two numbers to be equal, you have to have that the partial derivative of u with respect to x must equal partial of v with respect to y, and not only that, partial of v with respect to x must equal the negative of partial of u with respect to y. The resulting pair of partial differential equations are called the Cauchy Riemann equations. If u and v are the real and imaginary parts of a differentiable function, then these two equations must be true. Taking the contrapositive, if even one of these two equations is not true, then the function is not differentiable. Let's return to our example, the complex conjugate. The real and imaginary parts of the complex conjugate function are u equal x and v equal negative y. Partial of u with respect to x is 1. Partial of v with respect to y is not 1. It's negative 1. The complex conjugate fails to obey that first Cauchy Riemann equation, and that tells me it is not differentiable. The other Cauchy Riemann equation is true, but both of them have to be true in order to have a differentiable function. Let's be careful about the statement here. If the function is differentiable, then the Cauchy Riemann equations must both be true. If it's untrue that those two Cauchy Riemann equations are both true, then it's untrue that the function is differentiable. The converse is an interesting question. If I have a pair of functions u and v which obey the Cauchy Riemann equations, does that imply that u plus iv is differentiable. We'll come back to that later on. In the meantime, I hope everybody has a good day. I'll talk to you again soon.